So good morning, everyone. As you might heard from Andy's talk yesterday, I'm one of his not so successful students. Yeah. So yeah, and I blame him for that because apparently he failed to tell me that I need to move on to from my PhD thesis to work on something else in order to be successful. Yeah, so being Andy's student is not an easy job, as you can see. Even long after your graduation, you still feel the pressure. So back to the talk. Here is a list of my co-authors. I would like to thank them all for their significant contributions to the work, especially Andy, who has dragged me into the field. So here is the outline of the talk. First, a very brief introduction, as many of the characteristic or important facts, important things has been discussed yesterday by Tom and Andrew when they discussed about interactions around those non-magnetized obstacles. So I'm going to focus on the model, which is a global model. It's a multi-species MHD model that we have applied to Venus, Mars, and Titan. I will show some results of those and their comparisons with observation. This model has been recently improved to a multi-fluid MHD model. I will also discuss about the importance of multi-fluid effects around these three objects. The talk will be concluded with a short summary. So you've seen this plot several times. Venus, Mars, and Titan, they are all non-magnetized bodies and with substantial atmosphere. So the main things that I want to re-emphasize here is that the interaction region is really happen very close to the obstacle. So the upstream plasma flow would interact in a much more direct way with both the neutral atmosphere and the ionosphere. The solar wind can directly interact with neutrals through collisions. Some of them might result in creating of new particles, which are subject to be picked up by the solar wind. The upstream plasma also interact directly with the ionosphere, and this ionosphere will induce, because it's highly conducting, there will be currents induced try to exclude the magnetic field from penetrating into the ionosphere. And whether or not it can completely stop this penetrating depends on the ratio of the solar wind dynamic pressure and the ionospheric thermal pressure, as Tom mentioned yesterday. Due to this induced currents, there will be a region outside this magnetosphere with increased magnetic field, which sometimes we can call it an induced magnetosphere or magnetic pile-up region or magnetic barrier. And this region, of course, will directly interact with this ionosphere through transport of particles, momentum, and energy. So to study self-consistently how this ionosphere interacts with the upstream plasma, we need to know the composition of this ionosphere are quite different as compared with usually the upstream plasma flow. Here I'm showing the ionosphere of Venus and Mars. As you can see, they have very similar ionosphere. The main composition in both ionosphere are O2 plus at low altitude, and the important is O plus in Venus and CO2 plus. You can see the main composition of the ionosphere is different than the solar wind. So the method that we are using to simulate this interaction is a multi-species single fluid MHD model. This method was first introduced by Taraka in 1997, where he simulated two-fluid and two-component interaction for Venus. And the idea, even though the model has been improved, but the equation that solved in the model is similar. So we have a continuity equation which compare with the normal MHD model. We have also the source term, which can calculate the density change caused by chemical reactions. So if you neglected the velocity in the lower ionosphere, it's basically a chemistry model. But this velocity will become important at high altitude when the solar winds come in. And this is calculated through momentum equation. We included the momentum loss due to both ion-neutral elastic collision and chemical reactions. We also included the energy loss due to chemical reactions and ion-neutral elastic collisions in our energy equation. So the model is solved using Michigan Veteran's code, and I'm sure you never heard about it this week, especially this morning. So here is the normal setup of the simulation, and I'm using Venus as an example. So we solve for 4 different ion species, which is the main solar wind composition, and those are the 3 main ions in Venus ionosphere. And we also provide use the neutral as a background to provide the chemical reaction rates that needed to track the density. The main challenge of this global model is, of course, we want to resolve the ionospheric structure. So we need very high resolution in the ionosphere, and preferably we want this resolution to be comparable to the neutral scale height. So in the case of Venus, this resolution is about 5 kilometers in the ionosphere. Of course, this grade will extend, get coarser as you move away from the obstacle. And we choose the angular resolution, in this case, to be a constant value. Venus is the most computational expensive object because the high gravity, so the neutral scale height is much smaller as compared with Mars and Titan, and also the body size is larger. For Venus, we included about 5 million cells, and about half of that are inside the very close region to the body. We set the inner boundary condition to be at a very low altitude. In this case, it's 100 kilometers. It's well below the ionospheric peak region. So we can minimize the effect from the inner boundary. And we set all the densities to be in their chemical equilibrium. We included both the solar zenith angle effect, so you have a day-night asymmetry, and also the optical depth effect. We applied absorbing boundary for both velocity and magnetic field. As some of you might remember that the interaction also depends on the solar cycle condition. So here I'm showing 2 different cases. On the left is for solar maximum condition, and on the right is for the solar minimum condition. So the shock location according to Pioneer Venus and Venus Express observation varies for these 2 different conditions, because at solar maximum you have a strong ionosphere, so this provide a larger obstacle to stand off the solar wind. And at solar minimum, the ionosphere is relatively weak. The boundary, as indicated here, for solar minimum and solar maximum, for solar maximum is about 1.44 at subsolar points, and the solar minimum is about 1.33. As you can see, our model can self-consistently reproduce that the change of this plasma boundaries during different solar cycle conditions. And this figure shows, give you idea about how the field lines drape around the obstacle. So this is an upstream view, and this is what you look from downstream. This gray iso surface represent density contour with a planetary O plus density of 50 per cubic centimeter as an indication for the Venus ionosphere. As you can see, in this side, this ionosphere is very close to the obstacle. It's about 400 kilometers along the subsolar line, but extends to a much further distance down the tail, up to about 5 Venus radii. So you can see how these field lines they wrap around the obstacle and they slip over downstream to the night side. But an interesting feature I want to draw your attention is here. You see this kink of the field lines. This is because when the plasma, if they closer to this obstacle, then they will be heavily mass loaded by planetary ions. So they will be moving much slower as compared with the plasma that is further away from the planet. So this will cause this shape of the field lines. And also, these dripped lines will exert a G cross B force down the tail to accelerate the plasma to large distance. We also compared our simulation with Venus Express observation. This is a case that we selected 2006, day 152. So here I'm showing the magnetic field comparison. The black line is from the data, and the blue line is the MHD model. You can see the model matches quite well with the observation for the inbound shock, the outbound shock, and also the current shear crossing. It's about the same time. So and also the magnetic pile-up magnitude agrees quite well with the observation. But also you may notice there's a discrepancy. This happens in the region that is at near the closest approach at altitude below 200 kilometers. And we think that this field could be a fossil field that was diffused into the lower altitude during a different solar wind condition. And I will talk about the formation of the fossil field later when we talk about Titan. Move on to Mars. So this is the magnetic field and the velocity contour for Mars for solar maximum condition. As you can see, also we reproduce quite well the plasma boundaries around Mars. So if you look at the interaction, it's actually quite similar to what you have for Venus, except in this region, you see these red patches. These are due to this, the existence of the localized crustal magnetic field. So those crustal fields will also have effect on the ionospheric structure. Here, I'm showing the comparison with along Viking trajectory. So the dotted line are from the only in situ plasma measurements that we have to date from Viking, and the solid line are from the model result. As you can see, along Viking trajectory, we get quite a good agreement. But the thing that I want to draw your attention is comparing those two plots. So if you, in a non-magnetized obstacle, you expect that the ionosphere behave more or less the same when you have the same solar zenith angle. But here, you can see the density profile are quite different. In the southern hemisphere, where the crustal field is stronger, this crustal field will help to stand off the solar wind. And as a result, this ionosphere can extend to a high altitude. While in this case, the ionosphere is much more compressed. So I showed the simulation for a steady state where we choose a crustal field to be facing at toward the sun at constant at a certain angle. But we know that this plasma interaction is not really steady. There's also some statistic study showing that. Thank you. Showing that the escape rate will vary when you have enhanced pressure. But those statistic study cannot tell us how this ionosphere will respond to this pressure enhancement. Here we use a time-accurate mode to study how this ionosphere will respond to this idealized pressure enhancement case. So we have a pressure that is constant for before 2, and then suddenly we increase to 4 times larger its normal value, and then lasted for 30 minutes, and then drop back to its normal value. And here, this color showing how the escape fluxes will vary during this pressure enhancement case. So the most important message here is there's a fast initial response to the pressure enhancement, but there's also a long time recovery. It's about 2 hours in the case, and the recovery time is longer for the heavier ions. Here I'm showing how this ionosphere will respond to this pressure enhancement. As you can see, this is the ion density profile during quiet time, magnetic field, and the velocity vector. So when we enhance the pressure, this ionosphere will be compressed, and the magnetic field and the velocity will also have larger variations. Also, during the expansion phase, you can see a huge extension of the ionosphere. It extends to more than like 800 kilometers. The question about how, as we know that crustal field is not steadily facing toward the sun, it's actually rotating. So we also use our model to study how this crustal field rotation will change its interaction picture. As you can see here, as the planet slowly rotates, the induced field varies also slowly with this rotation. So this is a case that we did to compare with MGS observation. So we set the rotation axis to be exactly the same case as the state, and we then compare our model result with MGS observation. As you can see here, even though we don't know the solar wind condition, so in the simulation we assume the solar wind to be constant, we got a surprisingly good agreement between data and the model along these 12 different orbits. The agreement is especially good for the magnitude of magnetic field. This tell us that indicates that the model is doing quite well, and also the solar wind pressure is fairly steady during the day. The correlation for the components are not as good, mostly due to the IMF direction change during the day. And this is a zoom-in view of the comparison. You can see our model is doing a very good job near the strong crustal field region. The difference between this 22 UT is likely to be caused by the IMF rotation, but the field strength is not varying significantly, indicating the solar wind pressure is fairly steady. So move on to Titan. As Joe mentioned the other day, Cassini has made more than 90 Titan flybys, and lots of them are very interesting. And we have did some studies for quite some of those flybys. So, but I don't have time to show So I picked the one that I favor the most, which is the T32 flyby. This is happened when Titan is located at about 14 SLT. This is very close to the magnetopause, and during this flyby, Cassini actually see that Titan is moving across this magnetopause, as indicated by this magnetometer observation showing here. So before 1730, the field is pointing southward, meaning that Titan is inside Saturn's magnetosphere. But you can see a sudden change of the field afterward, so indicates that Titan is moving outside the magnetosphere. So we did a simulation to study this case. An interesting thing is what you may notice here, where the field orientation very close to Titan has an opposite orientation with the ambient field. And this is first proposed by Fritz Neubar, and those he indicates that those fields could be formed during the interaction with happened at the time before the with previous magnetic field. So here we've shown how this fossil field is trapped into this ionosphere. So we use a very simple current sheet to represent the magnetopause. So as you indicated by this purple line, this is indication for the interface between the new old field, which is a magnetospheric field, with the magnetosheath field. So they have opposite orientation. As this interface approaches Titan, it will distort it, wrap around the Titan, and eventually this interface will break. And inside this interface, you will have a region which contains a fossil field. You can see the field orientation inside this region is opposite to the ambient field. So we also compared with data along this flyby. You can see we get a pretty good agreement for both magnetic field and the plasma data. Okay. So move on to the multi-fluid model. This is work recently done by Dela. And she first applied it to Mars. So the important term here is here, which doesn't appear in the single fluid model, and this is the term that is responsible for the flow separation along convection field direction. So here I'm showing the comparison for single fluid model versus multi-fluid model. In the case of Mars, these are the density plots in the UE plane. So the convection electric field direction is pointing northward. You can see, compare the single fluid and the multi-fluid, there's the density pattern are quite different. You see a huge plume coming out from the positive E direction. We also did a similar comparison for Venus. So the interaction pattern are quite similar to each other. There's some subtle difference, but overall the multi-fluid effect is small at Venus. Move on to Titan. So this is what we have for the when we're using single fluid MHD model, and this is for the multi-fluid model. You can see the interaction region increases a little bit, and also you can see this asymmetry of the pile-up region compared with a single fluid model. And we also use the model to study how this different Titan local time will affect this interaction. So this is the case that the sun is coming in the same direction as the daytime ionosphere, and this is the opposite case where Titan is located at morning sector. You can see this multi-fluid model could produce very different patterns for the heavy ion flow. And we also see that when we calculate the escape fluxes, we also found that the escape fluxes vary significantly for those different cases. We see larger escape for the heavy ions during this case, but we see much less ion escape for the morning sector. So here is the summary. Since I'm running out of time, I'm not going to go through it. Okay, I.
It's okay. Good job.
Okay, thank you. Thank you.
Anyway, so we have, yes, Jim.
Yes.
Coming over there. I was extremely interested in the solar cycle variations you were showing in the global flow pattern. In particular, as you mentioned, the Venus bow shock, its total distance from the center of the planet changes by almost 30% from min to max, while the while the ionopause might change by maybe 5% or 3%. It's quite small. Were you able, I wasn't clear on, so you're reproducing the modulation in the bow shock. Most people have felt that this is some combination of charge exchange or mass loading because of the distribution of the neutrals or possibly electron impact ionization at lower altitudes. Could you tell me just a little bit about what you think causes it in your simulation, and also whether or not you found any modulation of the bow shock at Mars with solar cycle? Because observationally, I don't think we've seen any at Mars.
Yeah, I think in the case of Venus, there's two factors that actually move the bow shock location. One is the ionosphere. It does become stronger during solar maximum condition. Another difference is at solar maximum condition, the ionosphere is strong, so there's less penetration of the magnetic field from the solar wind. But usually at solar minimum condition, the IMF would penetrate into lower ionosphere from a magnetized ionosphere.
I love it. That's what was in my dissertation at UCLA.
Okay.
Chris Russell hated it and insisted it had to be more mass loading at high altitudes. The second part, do you see any of this at Mars?
I think the answer is yes. We did also simulations for Mars during solar maximum and the solar minimum condition. But I think the variation of the bow shock location in the case of Mars also depends on the crustal field location. So if you facing the crustal field toward this strong crustal field toward the sun, then the shock location would be further away. So, I mean, you see much larger variation when you look at the shock location at Mars. But yes, but there's, the model does predict there's some variation during different solar cycles, even for Mars.
All right.
Okay.
Tom.
There was a Harvard Don, I think by the name of McElroy, who felt that photodissociation of molecules was able to account for the escape from Mars. Is that still, I know you had some chemistry in your model, so I thought you might have evaluated whether that was still a viable.
Yes, I think that's a very valued point. And we also found that when we when we do these global simulations, our model are also sensitive to the neutral profile that we put in. So if we use different neutral models and change the photoionization rate, you will get a totally different answers for the escape rate. So we're looking for MAVEN to give us more information about the neutral profiles to better constrain the model.
Thanks.
Yeah.